Magnetic field. So a little bit of history. The term magnet comes from an ancient Greek city of Magnesia, at which many natural magnets were found. We now call natural magnets lodestones. Lode means to lead or to attract, which contains magnite, a natural magnetic material Fe3O4. Pliny the Elder wrote of a hill near the river Indus, now Pakistan, that was made entirely of a stone that attracted iron. Chinese around 121 AD knew that an iron rod that had been brought near one of these natural magnets would acquire and attain the magnetic property, and that such a rod, when suspended from a string, would align itself in a north-south direction. Use of magnets to aid navigation can be traced back to at least the 11th century. So what is it? Basically, we knew that the phenomenon existed, and we learnt its applications later. However, we did not understand it until 1819. Danish scientist Hans Christian Ørsted in 1819 observed that a compass needle in the vicinity of a tiny wire carrying electrical current was deflected. Finally, a connection between electrical and magnetic phenomenon was found. In 1831, Michael Faraday discovered that the momentary current existed in a circuit when a current in a nearby circuit was started or stopped. Shortly after, he discovered that the motion of a magnet towards or away from the current would produce the same effect. Hence, he concluded that both of these should be similar or related. So what is a magnet? A magnet is an object that attracts certain material, usually objects made out of iron or steel. Magnets do not attract things like paper or lead or cork. So some properties of a magnet: for every north there is a south pole. Every magnet has one north pole and one south pole. Magnetic field lines leave the north end of a magnet and enter the south end. If a bar magnet is broken into two pieces, each piece will again form a north pole and a south pole. If you take one of those pieces and break it down into two, each of the smaller pieces will form again a north and a south pole. No matter how small the pieces of the magnet become, each will always have a north and a south pole. No monopoles are allowed. It has not been shown to be possible to end up with a single north pole or south pole, which is called a monopole. So as soon as you break a magnet down, each of those two become a north and a south and a north and a south. Then if you break them further down, you cannot just get a north pole or a south pole separately. Some theorists believe that magnetic monopoles may have been made in the early universe, and so far we have not detected any. Concept of fields. Michael Faraday realized that a magnet has a magnetic field distributed around itself. Basically what he thought was that it has something around it, just like an electrical field. A magnet has something around it that others, when they are brought into the presence of it, experience either attraction or repulsion. So a magnet, and he called those fields, that field. So magnetic field lines describe the structure of the magnetic fields in 3D. If we place an ideal compass needle free to turn in any direction, then the needle will always point along the field line. In a compact bar magnet, magnetic field lines spread out from one pole and converge to the other. Magnetic force is strongest near the poles where they come together. This is what the field lines around a bar magnet look like. The direction of the field is from the north to the south. So around here, the magnet is going to go from this is what the direction of the field will be. It goes from the north to the south. However, on the inside of the magnet, the field lines will go from the south to the north pole, because it makes a complete loop around the magnet. These are the field lines around a magnet. If a north and a south pole are brought together, this is how the magnetic field lines align themselves. And if you have two north poles, they will repel each other, and this is what the field will look like. In the middle, there will be field cancellation. So, field that exists between two poles is nearly always uniform, and it does have some edge effects towards the side. However, in general, in our calculations, we will ignore edge effects. The spinning iron core of the Earth produces a magnetic field. The north pole of a compass needle is attracted to the geographical north pole of the Earth, and it is repelled by its geographical south pole. Earth is a large magnet with a magnetic south pole near the Earth's geographical north. The reason for Earth's magnetism are complex, involving standing currents in the Earth's molten interior. Earth's magnetic poles are separated somewhat from the geographical poles and move around a little bit as a function of time. There is evidence in geological records that Earth's magnetic field has reversed direction at varying intervals spaced by millions of years. That phenomenon is not well understood. There are some bacteria which also produce magnetic effects. For example, this one has a north and a south pole. So top 10 list about magnetism. This is what we all need to understand. There are north poles and south poles. Like poles repel, unlike poles attract. Magnetic forces attract only magnetic material. Magnetic forces act at a distance. While magnetized, temporary magnets act like permanent magnets. A coil of wire with an electrical current flowing through it becomes a magnet. Putting iron inside a current-carrying coil increases the strength of the electromagnet. A changing magnetic field induces an electrical current in a conductor. A charged particle experiences no magnetic force when moving parallel to the magnetic field, but when it is moving perpendicular to the field, it experiences a force perpendicular to both the field and the direction of motion. A current-carrying wire in a perpendicular magnetic field experiences a force in a direction perpendicular to both the wire and the field.